This is lecture 15, and in lecture 15, we're going to continue talking about convergence of random variables, picking up where we left off last time. So as a review of last time, we started talking about convergence of random variables, and we had talked about two definitions. We had kind of more in-depth talked about the first, which is almost sure convergence. And we say that a sequence of random variables, xn's, converge almost surely to some limiting random variable x if the xn's converge to x pointwise as functions for all sample points S in some set A, where the probability of the set A is sufficiently large, the probability is 1. So if the xn's converge pointwise to x, then for a large enough set where the probability is 1, we say it converges almost surely. One way you could think about this is that you could say xn of S converges to x of S for all S and A where A has probability 1. Or another way of saying this is that the probability of the set of S's such that xn of S converges to x of S. The probability of that set is 1. So we talked about this as a pretty strong condition and can sometimes be difficult to establish. And there are some other forms of convergence because random variables are such rich objects. We can treat them not only as functions, I'm going to talk about almost sure convergence, but they have other properties, and we can, the other properties, and we can define convergence in terms of other properties of these random variables. One of them that we kind of defined last time is called convergence in probability. And convergence in probability says that if I pick any positive threshold, epsilon, maybe I should write it this way. We say that the xn's converge to a limit x, and we put a p over our arrow, this to mean in probability, if for any threshold epsilon I choose, any positive threshold I choose, if I look at the limit as n goes to infinity of the probability that xn is more than or is less than epsilon, this goes to 1, or alternatively, if for all epsilons, I can look at 1 minus on both sides, the limit as n goes to infinity of the probability that xn minus x is more, that xn is more than epsilon away from x, and the limit goes to 0. So the idea with convergence and probability is that I'm just going to calculate, I'm going to pick a threshold, and I'm going to say, what's the probability that xn is within epsilon of its limit, x. And there's a sequence of those probabilities for x1, x2, x3, and if that converges to 1, we say xn converges in probability to x. Or alternatively, if I so I pick a threshold and I look at the probability that I'm more than epsilon, that xn is more than epsilon away from my limit x, if that goes to 0 as I increase n, we say that, alternatively, we say it converges in probability. So both are kind of useful ways of thinking about this. And this has to be true for all potential thresholds. So not just one threshold, but any threshold we choose, there's going to be some n such that I can make n large enough such that I can push this limit either to 1 or 0, depending on what I'm looking at. Now, notice here, I just want to point out, if you go back to our notes last time when we talked about convergence or almost sure convergence, we had said that that an equivalent way of saying that xn converges almost surely to x is that if I look at the way I was writing, which was the probability of the limit as n goes to infinity of these events, xn minus x less than epsilon, and that thing was 1. So here, xn minus x less than epsilon is some event. If I fix my epsilon and I fix n, then there'll be some part of the sample space where xn minus x is less than epsilon, and there'll be some part of the sample space where it's not. And these are going to be some kind of, ultimately, some kind of nested, presumably, sets. And you can kind of define a limit, which is kind of the union of these sets. And we said, so this thing is ultimately just some event, and you can talk about the probability of it. And if the probability of that thing is 1, that's an equivalent way of defining almost sure convergence. The reason I talked about that there is because we define this definition of convergence and probability, and that looks really similar to our convergence and probability. Convergence and probability switches the limit and the probability. So convergence and probability is the same thing as saying the limit of the probability of xn minus x less than epsilon is 1. So all we've done, switching from almost sure convergence to convergence probability, is we switch the limit and the probability. And you can't always do that. You can do that for certain sets, but that's not always possible to do. The thing that is always possible to do is that if I know 1, I can always bring the limit outside, but you can't always push the limit inside. And what that means practically is that almost sure convergence implies convergence in probability. So we're not going to prove that, but I'll write it as a theorem, and it's something that you should know as a fact. And the theorem is that if a sequence of random variables converges almost surely to a random variable x, then this implies that this sequence converges in probability to x. So almost sure convergence implies convergence in probability. Generally, the converse is false. So generally, in convergence and probability does not imply almost sure convergence. So what this means is that almost sure convergence is a stronger condition than convergence in probability, IP. So if we know something converges almost surely, we guarantee the convergence in probability. If we know convergence in probability, in general, and we'll talk about some specific cases where the converse does work, but in general, we don't know if it converges almost surely. So in some ways, in probability, convergence is weaker, which is what I claimed is true. And so sometimes things will converge almost surely, but sometimes they won't. But just because it doesn't converge almost surely, there might be a weaker form of convergence that we get. Okay, so let's consider an example of almost sure convergence. Now, this is going to be a little bit of a complicated example. Just going to need some space to write things down. So again, we're going to consider a sample space S, which is just my unit interval. And let's assume we have uniform density. And by that, I mean my well, we won't get exactly what that means, but we're going to assume we have a sample space with kind of uniform density. And I'm going to define a sequence of random variables, x1 of s. All right, so random variables are functions, so I can define them kind of as a function on this sample space, right? Not typically how we do it, but you can. I'm going to define as s plus 1. Cool. x2 of s, I'm going to define as s plus the indicator that we're in 0 to 1/2 of s. So we can maybe draw a little graph here. So this is basically my x-axis is s, and this is 2, and 1 is somewhere here. Basically, we get some kind of linear function, right? From 1 to 2. That's 0 to 1. That's x1 of s. And x2 of s, we can again draw a little picture here. 0 to 1, that's 1, that's 2. It's s plus a half, x plus the indicator that s is in 0 to 1/2. So if we're in 0 to 1/2, right, it will be s plus 1. And so it looks something like that. And, right, because at 0, it will be 1. And at 1/2, it will be 1/2. And then if I'm in 1/2 to 1, this indicator is 0, so it's just going to be s. So it looks something like that. So it's a little bit of a complicated scenario that's going on here. Let's define x3 of s is s plus the indicator that we're in 1/2 to 1 of s. Say something like that. And so basically I've divided up my interval in halves. x4 of s is s plus, and now I'm going to divide my interval up into thirds. I'm going to say here 0 to 1/3. x5 of s is s plus indicator I'm in 1/3 to 2/3. x6 of s is s plus the indicator that I am in 2/3 to 1. So you see I've divided up the thirds, and then I'm going to continue on. x7 of s is s plus, and I'm going to divide it up into fourths. So 0 to 1/4. Something like that, right? And I'm going to keep doing this. I'm going to go through the fourths, and then I'm going to go through the divide into fifths, and divide it into sixths, right? And I'm going to kind of build up this sequence of random variables. And let our limiting random variable, x of s, just be s, okay? And our question is, does this sequence, xn, converge in probability to x? So what do we need to do to show that this thing converges in probability? We can use maybe our second definition here. Doesn't really matter, you can use either, but let's use the second one. We say we want to look at that, at the probability that xn is more than epsilon away from x. So let's look at, let me write this down, right? We need to show, if we believe this converges in probability, we would need to show that if I look at xn, I look at xn, and I said look at the distance of xn to x, and I look at the probability that it's more than epsilon away, we have to show that the limit of this as n goes to infinity is 0. That is, I can choose my n large enough so that in the limit, the probability that xn is more than any finite threshold away from x is 0. Okay. So let's look at some of these objects. Let's look at, for example, xn minus x. Let's start with x1 minus x. What does x1 minus x look like? So this is x1 is s plus 1, and x is s. So this is surely just 1 everywhere. And, okay, let's look at x2 minus x, all right? This is going to be s plus this indicator minus s. So I'm going to lose that s, all right? So when I subtract off, I'm going to lose that. Oops, let's cross that red. I'm going to lose that. I'm going to lose that s if I subtract off my x here. And this will be the indicator. I'm in 0 to 1/2. Of course, I don't need my absolute value bars because it's all positive. So this is just the indicator. I'm in 0 to 1/2. x3 minus x is going to be, by a similar game, the indicator I'm in 1/2 to 1. x4, notationally cumbersome, x4 minus x is the indicator I am in 0 to 1/3. All right, we keep playing this game. x5 minus x is just going to be the indicator that I'm in 1/3 to 2/3, etc. All right, say dot, dot, dot. So if we plot these, what are these going to look like? x1 is just a function. So here's s, here's 0 to 1. This is this first difference. This is x1 minus x. And so that's that one. Let's do a couple more of these. 0 to 1, 1 somewhere. This is just the indicator, 0 to 1/2. So it's going to look like that. And then it's going to drop down to 0, right? Look at another one. 0 to 1. This is the indicator. We're in the second half of the interval, so it's going to be 0 for the first part, and then it's going to be 1 for the second part. And so what you see is that we're just getting these indicators of various segments, right? Let's just do it a little bit more. Then I divide my thing into thirds. So 1/3, 2/3, 1, and just going to be the indicator right in the first third, and then it's going to be 0 for the rest of it. Let's do one more, right? 0, 1/3, 2/3, 1. That's just going to be my indicator that I'm in this middle third here, right? So all you're seeing is it's basically these functions that are either 0 or 1. And I start off by 1 everywhere. Then I have 1 the first half, 1 the second half, 1 the first third, 1 the middle third, 1 the last third, 1 the first fourth, 1 the second fourth, 1 the third fourth, 1 the fourth fourth, right? So I'm just going to get these kind of functions, right? And certainly if we need to show for all epsilons, right? So I basically calculated this first part of this thing here. And I need to find the probability that this thing is bigger than an epsilon, right? And I need to find the limiting probability. Well, if epsilon is bigger than 1, which would be something like here, the probability that x is bigger than that is 0, right? My x is never bigger than that. My x is always either 0 or 1. So I'm going to get that would kind of be my epsilon threshold, all right? Something like that. In this case, it's easy to do this calculation. The probability that xn minus x is bigger than epsilon or bigger than or equal to, whatever, is 0 for all n. So certainly, since it's always 0, then my limit of a bunch of zeros is also 0. right? Bigger than, right? So that's easy. The somewhat harder case is that, and let's just change colors here, if epsilon has to be bigger than 0, but it could be less than 1, right? So what would that look like? So it'd be some threshold like that, and it's going to split all these like this, right? Okay. And so the probability is not 0, because sometimes, for example, in this last one, we have a portion of it where it's bigger than my epsilon. Or here we have that portion of it, it's bigger than my epsilon. In the first one, all of it's bigger than the epsilon, right? So it's not always 0. But we can do some calculations, right? So the probability that x1 minus x is bigger than epsilon is 1 for the first one, because x1 is always 1, and that's going to be bigger than any epsilon if their epsilon is between 0 and 1. For the second one, it's going to be 1/2. It's this first half. The third one, it's going to be 1/2 again, because it's the second half. The fourth one is going to be a third, a third, a third. So what we're going to get is something like this. Half. Man, so much notation. I guess you could say greater than or equal to, doesn't really matter. It's a half. And then I'm going to say this is going to be a third. That's going to third, third, right? And then it's going to be a fourth, right? As we continue down here. And so I'm going to just make the argument, this is kind of proof by intimidation, which is this has a limit of 0. So what I mean is that the limit as n goes to infinity, right? The sequence is clearly going to 0 as n goes to infinity of this thing. It's going to eventually hit, or in the limit, hit 0. It never actually achieves 0, but in the limit, it will touch 0. And so that covers the second case of my epsilon between 0 and 1, and the easy case is that epsilon is bigger than 1. And so we've shown what we need to show, which is that xn converges in probability to x, because this limit for any epsilon is 0. So that's, these problems can be a bit hard at the beginning here because we're working with random variables and treating them as functions, which is not something that we always, we did that a little bit back in 451, but then you kind of move away from treating these things as functions. And now we're moving back to treating them as functions, and it's a bit much to wrap your head around, right? You gotta think about, oh yeah, I can treat this thing as a function from my sample space, etc. So we've shown that this sequence of random variables converges in probability to x. And a question is, does xn converge almost surely to x? Now, we don't know. We have a theorem, and our theorem says that if it converges almost surely, then it converges in probability. But we don't know if it converges in probability, we don't know if it converges almost surely or not. At least we don't have any theorems yet to guide that intuition. So a second question is, does this thing converge almost surely to x? So let's look at this, this problem. Right? To establish almost sure convergence, what we need to do is we need to look at the set A, and this is going to be some event. So it's going to contain samples in our sample space, and it's the set of things where xn converges to x. So for which little s's is this true? And I guess we could say that xn converges almost surely to x if and only if this probability of this set is equal to 1. So if I pick any little s in my sample space, which is my unit interval, consider my sequence, x1 of s, x2 of s, oop, that's not a parenthesis, x3 of s, right, and so forth. What does this sequence look like? So if I go back up to my picture here, go back up to my random variables here. If I pick any s, this is going to oscillate between s and s plus 1. So it starts off as s plus 1, and then if I'm in the first half, so let's just pick, s is I don't know, let's say 1/8. So it's going to go 1/8 plus 1, 1/8 plus 1, 1/8, 1/8 plus 1, 1/8, 1/8, 1/8 plus 1, right? So if we pick any s, it's going to oscillate. X of s will oscillate between s and s plus 1 forever. Because as you can always pick something, it's going to kind of divide up the unit interval into more slices, and it's going to oscillate back and forth between those values. So it won't settle down. And therefore, it has no limit. So indeed, for all s, we get xn of s does not converge to x of s, and so the probability of A is not only not 1, it's actually 0. And thus we can say that xn, we can say, does not converge almost surely to x. And so that gives you a bit of a flavor of the difference. So here's an example where something converges in probability, but doesn't converge almost surely. Because you can get a probabilistic bound that will converge, but the functions themselves don't converge for a sufficiently large set. And so that's kind of the flavor of the difference. Okay. So that is 2 types of convergence we've talked about so far. And the third type of convergence that we want to talk about is called convergence in distribution. And we say that a sequence of random variables xn, so there's some sequence of random variables xn converges in distribution to a limiting random variable x if, or let me say, we denote it. So we say xn converges in distribution to x, denoted xn with an arrow with a d for distribution to x. If, well, I can say this very simply, the CDFs converge pointwise, i.e., so that's the real simple way of writing it, i.e., if f xn is the CDF of x, and f is the CDF of x, so f xn is the CDF of xn, and f is the CDF of x, then for all little x, we have that f, the CDF of xn at little x, converges to the CDF of x. Or this is saying f xn converges pointwise to f. That's the definition. So in some ways, convergence and distribution is, we don't necessarily need, it's not that the xn's converge pointwise. It's that the CDFs of the xn's converge pointwise as functions. So that's somehow how it's related, one kind of relation to almost sure convergence. So let's look at an example. In some ways, this is the nicest of them. It's like all you have to do is, get the CDF and the CDF converge in some kind of nice way. Then that's called convergence in distribution. The cumulative distribution function converges. So let's consider an example. I think the convergence distribution is somehow the nicest and makes the most intuitive sense. Almost sure convergence and hard, makes some sense. I think in convergence probability is more of a complicated condition, but convergence distribution is pretty nice. So let's assume we have a sequence of random variables xn, and their iid from uniform 0, 1. So here's my notation. We don't just have some capital N of them. We have an infinite number of these. 1, 2, 3, 4, 5, 6, x million, right? And let yn be the maximum of the first n of these. So if I goes 1 to little n, it's the maximum of the first n of these. So this is the maximum of first n xi. So y1 is just x1. y2 is the maximum of x1 and x2. y3 is the maximum of x1, x2, and x3. y4 is the maximum of x1, x2, x3, and x4, right? And our intuition is that if we look at a unit interval from 0 to 1, we're looking at the maximum of more and more and more uniforms. And so we expect the maximum to go to 1. As I get more x's, if I sample, let's say, an x here, and then an x here, and an x here, and an x here, and an x here, you notice as I'm drawing these, the maximum doesn't decrease, right? Right. So I'm just kind of pretending I'm uniformly distributing these throughout the space, right? You can notice that the maximum heads towards 1, right? And so the expectation is that the YNs converge to 1, that the maximum of these things is going to converge to 1. So before we talk about convergence and distribution with these, let's talk about maybe it's that the xn's converge in probability to 1. So I'm going to write this. What does that mean? Because before I've written that xn converges to x, maybe in probability. And what does it mean to say that xn converges to a number in probability? So numbers are, in some sense, random variables. They're just degenerate random variables. This is what we call a degenerate random variable. So you can think of any number, I'm sorry, this is not the xn's. This is supposed to be theyn's, right? Somehow, number is a degenerate random variable where if I look at the PMF, it's just, it's going to have all of its mass associated with this 0.1, right? So this is basically my PMF, my probability mass function. So you could have a random variable, where f of x is 1. If x is equal to 1, it's equal to 1, and 0 else. It's kind of like a number, but you can technically think of it as a random variable. It's just, it's a random variable where the probability of taking on 1 is 100%, right? And you can do this with any other number. You could have a degenerate random variable of 5. And so when I say statisticians are often lazy, and we'll just say, well, a yn converges maybe in probability to 1, when they really mean is it converges to the, to the distribution where the probability, converges to some y, where the probability that y is equal to 1 is 1. So you could call this a degenerate random variable, y. Doesn't really matter. So let's first see if we can establish. So our intuition is that these these y's, should get closer and closer to 1. And so maybe we can establish convergence and probability. And then we can talk about convergence and distribution and what that might mean here. So to establish convergence and probability, we have to look at, so we're going to call that degenerate random variable y. So typically you'd look at, say yn minus y. You look at it, say the probability it's bigger than or equal to epsilon, and you look at the limit in n as that thing goes, and you hope that that limit in n goes to 0. So this would show convergence and probability. This is what we want to show. And in our case, our y, our limiting random variable, is pretty simple, right? It's just a degenerate random variable at 1, so I can just replace that with the number 1. Supposed to be the number 1, right? And I want to show that the limit as n goes to infinity is 0. All right, that's my notation. Arrow, limit, and I've written n to say as n gets bigger. So that's just some notation. Let me just write that. Notation for limit as n goes to infinity, ... right? Because I'm lazy and I don't want to write that a bunch of times. Okay, so let's look at what we can show. So first of all, I can flip around the yn and the 1, and I can say this is 1 minus yn bigger than or equal to epsilon, right? Why do I do that? Notice that surely yn is always less than or equal to 1, right? Yn is the maximum of a bunch of uniforms of these x of n's. It's never going to be bigger than 1, because the x's can't be bigger than 1, so the maximum can't be bigger than 1. Said that several times. And so theyn's are always less than or equal to 1. And so if I flip it around and think of it as 1 minus yn, I can actually drop those absolute value bars, right? Because yn is always less than or equal to 1. And so I can rearrange this and say this is the probability, what do I want to say? That yn is less than or equal to 1 minus epsilon. And myyn's is the maximum of my xn's, of the first n of these things, of these x's. And so this whole condition is that the maximum is less than or equal to 1 minus epsilon. And what do we know, right? So let me actually just write that out, right? So this is the probability that the maximum of the first n of these x's is less than or equal to 1 minus epsilon. And if the maximum is less than or equal to 1 minus epsilon, they are all less than or equal to 1 minus epsilon. So I've made you hopefully beat that fact into your minds by this point. Now we can abuse this fact. So this is the same thing as saying that x1 is less than or equal to 1 minus epsilon, and x2 is less than or equal to 1 minus epsilon, and, my comma means and x3 is less than or equal to 1 minus epsilon, ... all the way up to xn is less than or equal to 1 minus epsilon, right? And my x's are independent. So this is the same trick I play every time I do these maximum calculations, right? You've hopefully seen this a couple times now. My x's are independent, so I can say that this is just the product. Let's say I goes 1 to little n of the probability xi is less than or equal to 1 minus epsilon. Independence gets me that, right? And what's my next trick? They are all identically distributed. Identical distribution, and they're uniformly distributed. So the probability that xi is less than or equal to some number a is just a, as long as a is between 0 and 1, right? That's just kind of what it means to be a uniform random variable, and the x's are uniform. And so each of these, I goes 1 to n. Probability x of I is less than or equal to 1 minus epsilon. Surely it's just 1 minus epsilon. And so that's n times, so that's 1 minus epsilon to the n. And this is tacitly making some assumption here. So we'll just say this is making the assumption that 1 minus epsilon is less than or equal to 1. If 1 minus epsilon is bigger than 1, we're going to get a bunch of 1s, right? If the probability that xi is less than like 5 is 1, right? So if 1 minus epsilon were bigger than 1, this thing is just going to be 1 a bunch of times. But is that right? Did I do that right? Yep, that seems right. If 1 minus epsilon is less than 1 here, then this thing, surely, as n gets large, goes to 0, right? Because we're going to get 1 minus epsilon, which is some number between 0 and 1, we're going to raise it successively higher and higher and higher and higher powers. And eventually that's just going to get 0. It's like, what's 1/2 squared is 1/4, 1/2 cubed is 1/8, 1/2 to the 4th is 1/16. It goes smaller, smaller, right? So any number between 0 and 1, if I raise it to higher and higher powers, is just going to shrink. And so this thing surely shrinks down to 0. Now I had this condition here that 1 minus epsilon is less than 1. And how can we reword that? That is 1 minus epsilon less than 1 if we move the epsilon over, and we subtract off a 1. What's the equivalent condition in terms of epsilon there? It says epsilon is bigger than 0, so maybe that's a that's a fine condition, right? This is surely just the condition. When is 1 minus epsilon less than 1? Well, if epsilon is positive, then we're good, right? Because 1 minus epsilon would be less than 1. So this is the same thing as saying epsilon is bigger than or equal to 0. And that's what we wanted to show. So actually that condition isn't really an important condition here, right? Because that's the whole condition we want. We want for any positive threshold epsilon, this thing goes to 0. And that seems to be reasonable. I guess more properly, our condition is, right, in order for this to be true, we said a has to be between 0 and 1, so it really should be 0. So really like that, which says that epsilon is between 0 and 1. Okay, so this is true for epsilon between 0 and 1. I guess not for all positive epsilon. However, if epsilon is bigger than 1, so we showed it for a subset of these thresholds. If epsilon is bigger than 1, what happens? We want the probability that 1 minus yn is bigger than 1. That's never going to happen. This thing is 0 for every n if epsilon is bigger than 1, right? Is there any time that yn is going to be more than 1 away from 1? No, because yn is between 0 and 1. So that kind of established it for the second case. Of course, if it's 0 for all n, it's 0. The limit is 0. So in any case, in both cases, this is kind of case 1, that, and then this is kind of case 2. In both cases, there's always this kind of annoying, it's like a analysis class. There's always these really annoying edge cases you're thinking about, okay, but practically the hard case is when epsilon's between 0 and 1. And that's often true. In both cases, however, we showed that if we look at the probability that yn minus 1 is bigger than our threshold, this thing in its limit as n goes to infinity is 0. And so that shows that these yns converge in probability to our constant, or a degenerate random variable 1. Which is nice. Okay, so that gives us some intuition about what's going on. It shows us that okay, these things actually do kind of nicely converge in probability to the value we think they should. And I guess the next case is we can look at, can we get this thing to converge in distribution to something? So the easiest thing to think about is, can we show, does yn converge in distribution to this degenerate random variable 1? Now, what this means is that we get some CDF of yn, and we need to show that it goes to the CDF of our limit. What's the CDF of our limit? What's the CDF of our degenerate random variable? Our degenerate random variable has all of its mass associated at the number 1, and so we're going to get a jump from 0 to 1 like that. So this is what the CDF of our degenerate random variable 1, or our limit is, right? Is this kind of step function that just steps from 0 to 1, goes from 0 to 1 at 1. Cool. So can we show that the CDF of these yn converges pointwise to this thing? The answer is yes, we can show that. So how do we do that? We need to get the CDF of the yn. We have the CDF of f, so let's get f of yn. Let's say at some value little y. And I guess for continuity, we could call this f of little y. Doesn't really matter. So this thing is the probability, right? Our CDF, if you remember, is the probability that yn is less than whatever value, little y. And we can play our same games. This is the probability that the maximum of our first n x's is less than or equal to little y. And if we're going to go through this a little quickly, but if the maximum is less than or equal to little y, this is the same thing as all of them, that x1 is less than or equal to y, x2 is less than or equal to y, xn is less than or equal to y. And by independence, so let's say by independence, it's supposed to read, that's independence, we get that this is the probability xi is less than or equal to y. It's the product of all of those, right? We can just factor that, where I goes 1 to n. And these things are, again, uniform. These xi's are uniform. What's the CDF of a uniform? Of xi, the CDF of a uniform looks something like this. Say 0, 1, 1, 0. The CDF of a uniform looks, it's 0 up until 0, it's 1 after 1, and it has a slope like this. Here the slope is 1 in the kind of interesting region, but it's kind of this kind of piecewise linear function where it goes 0, it linearly steps up until 1, then it flattens out. That's the CDF of a uniform. So this is f xi of, let's say, y. And so as long as little y is between 0 and 1, right, as long as little y is in this region here, this is just what? Each of these are y, so this becomes the product. That goes 1 to n of y, which of course we have a name for. Technically, we have to consider all cases. Let's just say let's be really technical, if y is between 0 and 1, we're just going to get y n times, so it'll be y to the n. If y is bigger than 1, we're just going to get 1 each time. And if y is less than or equal to 0, we're just going to get 0. So that's the CDF. And what is the limit of this thing as n goes to infinity, right? So this is the CDF, ultimately, Fyn. And we wanted to show that that thing converges to the CDF of f, which is the step function. So what does this thing look like? The limit as n goes to infinity of this thing. We have our three cases. Y is bigger than 1, y is less than or equal to 0. Those won't change. Right, that's just going to be 1 and 0. And in the case where y is between 0 and 1, the kind of interesting case, if this is a number between 0 and 1 to successively higher and higher powers, this thing is going to go to 0, right? This thing is going to go, as n goes to infinity, to 0. And so we can actually summarize this thing. So this is where, like that. So it's actually 0 up until 1, and then jumps to 1, which is exactly this CDF. This is exactly f of y. And so what we've shown here is that if I look at the CDF of my YNs, these converge kind of pointwise to the CDF of my degenerate variable 1. And so what that shows is that Yn converges in distribution. Yn converges in distribution to 1. So this actually motivates a more general theorem. Because we saw, so what we've shown, so there's your kind of first example of convergence and distribution. Not the most exciting example because it's kind of this degenerate distribution, but we saw that, at least in this case, we showed first that it converged in probability to 1, and indeed, you can then show that it also converges in distribution to 1. And the more general theorem is that convergence in probability implies convergence in distribution. So, real simply, if my xn's converge in probability to a limiting random variable x, then the xn's converge in distribution to that same x. So the corollary of this theorem is that we now know a certain chain of convergences. That is, xn converges in almost surely to x implies that xn converges in probability to x implies that xn converges in distribution to x. So almost sure implies in probability implies distributional convergence. And that's the chain that you should memorize. So that's the chain that the kind of really important convergence chain. And it shows that, and we're not going to prove that theorem, but it shows that the kind of which of these is strongest. Almost sure convergence is the strongest form of convergence. Slightly weaker is convergence in probability, and weaker yet is convergence in distribution. So if it converges almost surely, it converges in probability, converges in probability, converges in distribution. The other way, generally not true. Convergence in distribution generally doesn't imply improbability, and improbability generally doesn't imply almost sure convergence. We will see some special cases where we can get this reversal of these, but the general rule is that you can only go this one way. So distributional convergence is the weakest form, improbability is kind of the middling form, and almost sure convergence is quite a strong form of convergence. So we saw this example of distributional convergence, and it might be interesting, and maybe this is a good way to close out this lecture, is to revisit this example. And because, for our distributional convergence, we gotta have really uninteresting distribution. Converge to a degenerate distribution. That's not very interesting. It'd be more interesting if we could get something, some other kind of distributional convergence. And so we can converge to something kind of not degenerate. Let Zn be n times 1 minus my Yn. So this is continuing our example where my Yn is the maximum of my xn's and my xi's, let's say. And my xi's are iid from a kind of uniform 0, 1. So let's just look at the CDFs of these z's and see if we can figure out a distributional limit. So the question is there an interesting distributional limit? So let's see. Let's just look at fzn at some value z, right? So this is the probability that zn is less than our value z. So that's not a 3, that's a little z. It's a little script z, which is the probability. What's z? It's n by 1 minus yn. And we want to look at the probability. Whoops, that's less than or equal to little z, right? So for distributional convergence, all we got to do is we got to look at the CDFs and we can figure out what that we can see that converges, that the CDFs converge to a known CDF. Then we basically know what the distributional convergence is, because that's all you need to actually show for convergence and distribution. So let's just do some algebra now, right? This is the same thing as the probability that 1 minus yn is less than or equal to z over n, right? Or probability, I can move my yn over and move my zn over. This is the probability that, let's say, yn is greater than or equal to 1 minus z over n. It's supposed to be a z, starting to look like a 3. Okay, right? Okay, purely algebra. And I can, of course, look at the complementary probability of this. So I could say this is 1 minus the probability that yn is less than or equal to 1 minus z over n. Why do I want to do that? Because my yn is a maximum, and I know something about the probability of maximum is less than or equal to something, right? I've done this trick 3 or 4 times now. This is the probability of the product. I'm just going to skip some steps where I goes 1 to n of probability that my xi is less than or equal to 1 minus z over n. Right? And I get that because the yns are the maximum and the xn's. Probability the yn is less than or equal to whatever quantity is probability all the xi's are less than or equal to that. The xi's are independent, etc. We've done this several times now. And again, recall that my xi's are uniform 0, 1. And so we know what their CDF is. And this is basically the product of, one way to write this is that this is 1 minus the product, I goes 1 to n, of the CDF of xi at 1 minus z over n. And my CDF of xi is just, let's say at some value t, doesn't really matter, whatever, is, right? So the CDF is a uniform CDF, right? And it has this form where it's basically t if t is between 0 and 1, it's 0 if t is less than 0, and it's 1 if t is bigger than 1, right? So that's my CDF of a uniform. What do I get? I get 1 minus, and all of these things are the same, so I can just say it's the CDF of any of my xi's at 1 minus z over n, right? They're all identically distributed. It's CDF of any of them to the nth power, because that probability of that CDF is going to be the same for all of them. So I can certainly do that, and then I'm just going to plug this in. Well, it's going to have 3 cases, so let's break it out into its 3 cases. Okay. Case 1, which is 1 minus z over n is between 0 and 1. So let's just write that out. All right. In this case, I'm going to get just my CDF is just whatever the argument is. It's 1 minus z over n to the n. Cool. The second case is that 1 minus z over n is negative. And in that case, sorry, I got to get this right. It should give me 1, right? Because I have 1 minus a bunch of zeros. And on the flip case, if 1 minus z over n is bigger than 1, I'm going to get 0 because this part will be 1 then. We can rewrite these conditions. So 1 minus zn is bigger than 1. That says, surely that means that z over n is less than 0. And if 1 minus zn is less than 0, that means z over n is bigger than 1. I'm just going to rewrite these all in terms of z over n. And I can just kind of flip things around here. This is the condition where z over n is between 0 and 1. So that's just, I'm just simplifying the conditions to be in terms of z over n. And so what's the limit of this? So the question is, what is the limit of this, right? What are we even calculating, right? We're calculating the, a whole bunch of steps up, the CDF of my z's. And I got down into this form. And if I could identify that the CDF converges to a known CDF, then I basically would be able to say that the z's converge to some known distribution, converge in distribution to that known distribution. So what does this look like? Here's some recollection from sophomore year of high school, Algebra 2, something like that. If I look at the limit as n goes to infinity of 1 plus 1 over n to the n, that is E, our favorite Euler's number, right? So let's say that's 1. This formula can actually be expanded. If I look at the limit of 1 plus c over n to the n, that is e to the c. And what this means that if I look at the limit as n goes to infinity of, it starts to look like it, 1 minus 1 plus c over n to the n. This is 1 minus e to the c. Okay, so that's just some recollection from our limit definition of e. And so if I want to answer this question, right, surely the limit as n goes to infinity of these two things is just going to be uninteresting, right? So as n goes to infinity, we're basically getting 0 for these two cases are going to go away. So that's not interesting. But the first case here, as n goes to infinity, we can let our c be negative z over n. I'm sorry, negative z. And then our fzn of, what's our value in there? Fzn of z, right? This thing is basically 1 minus 1 plus negative z over n to the n, right? 1 minus 1 plus negative z over n to the n, and that thing surely then will converge to 1 minus e to the negative z. So what I've shown here is that the CDF of my z's converges to this function. Is that a known CDF? Yes, it is. This is the CDF of an exponential random variable with lambda equals 1. So what we can say is that Zn, which is n by 1 minus yn, converges in distribution to, I'll just write it like this, an exponential one distribution. So this is a nice cute little example where my convergence is not to a degenerate distribution. Exponential 1 is not some kind of degenerate distribution. It's a real live distribution. And the way that I got that is I properly scale it. So my YNs converge to a degenerate distribution. If I properly scale it, basically, I take 1 minus it, but that's not a huge deal. If I properly scale it by n, I get convergence to a non-degenerate distribution. It converges to something with, non-zero variance. And this is a game we're going to revisit when we start talking about the central limit theorem, because this is basically what the central limit theorem will do. So we'll hold off on that, but just put a pin in this when we come back to that. But this is a nice example of convergence and distribution, and it's not too bad, but maybe not the simplest, but where we get a random variable converging to some other kind of random variable in a distributional sense. So I think the last thing that we should do here when finishing off is just to mention, so we had this theorem. We know that almost sure convergence implies convergence and probability implies distributional convergence. And we said that generally the converse isn't true. There is, however, a partial converse to this, and we basically saw it in this example, or the previous part of this example. So generally, you can't say that distributional convergence implies convergence and probability. However, if we have a series of random variables xn, and they converge in distribution to some constant distribution. So this is a constant / degenerate distribution at C. Let's say concentrated at C. At some number C. If we know a sequence of random variables converges in distribution to a constant, to a degenerate distribution, then we actually do know that it will also converge in probability to that constant. So it's a partial converse, and so it only really works when we have a constant distribution. But convergence and distribution to a constant implies a convergence distribution to a convergence and probability of that constant. Notice that the other way is already true, because we already know that convergence and probability to a constant would imply that it converges in distribution to that constant. So what this says is that if the limit is constant, that is, if our random variables converge to a constant distribution, probabilistic convergence in probability is equal to convergence in distribution, let's say. That these two concepts actually coincide with each other when we converge to a degenerate distribution. And we saw this not in this part of the example, but if we go back up to the previous part, we saw that the YNs converged in distribution to the degenerate distribution 1, and also we had originally proved that they converged in probability to that degenerate distribution. And so if we actually had known this theorem, we know that they're the exact same concept, that convergence to a constant distribution is basically the same. It doesn't matter if you're talking about probability of distribution, they are equivalent modes of convergence. So I think that's probably a good place to stop here. Not do too much and let you digest this, but we've done, these are the three major modes of convergence: almost sure, probability, and distribution. And you should definitely know what implies other, and you should know, say, this partial converse theorem. But we're at about time here, so let's call it here.